So, I think we're gonna start. So, hello everyone, and welcome to the fifth event in our special online meetup series hosted by the Web3 Developers Underground community. Before we dive in, let me please briefly introduce you to our community. We are a community of Web3 developers founded on the open source values by Shaoli Rejwan and Roy Yosherov. Since our inception 3 years ago, we've consistently hosted in-person events, bringing together some of the brightest technical minds in the space. As many of you may know, we've recently expanded to an online meetups, and we're committed to delivering top-tier technical content on the global Web3 community. We're thrilled to have you with us today. So to make sure, please make sure to follow all our platforms on X, Luma, Meetup, YouTube, Telegram, and more to stay in the loop for future events and updates. A special thanks to our community sponsor, Master KVC, an early-stage venture capital firm focused on infrastructure and deep tech across Web3 ecosystem, with a team of 16 world-class cryptographers and technical experts led by their managing partner, Shaoli Rejwan. Master Key operates across all major global crypto hubs. And now, without further ado, I'm honored to pass the mic to Slava, the CTO and co-founder of Strum Networks. Slava, the stage is yours. Just a moment, Slava. I think you're still on mute. Just a moment. I think you're still on mute. It's okay. We'll take two moments to see it works. Oh, now we can hear you, Slava.
Yeah, that was a problem with my headphones. Sorry about that.
No problem.
Yeah, hello everyone, and thank you, Amit, for inviting me. Really honored to be here. So my name is Slava. I'm CTO at Strum Network, and at Strum Network we are building Bitcoin liquid staking protocol. And I'm today's topic. What I choose it's Schnorr signatures. So we particularly using Schnorr signatures in our projects. So and while we were building our project, we learned about Schnorr signatures a lot, and I found it really fascinating and cool topic in cryptography, and which might be particularly very useful for any Web3 development that is happening right now. So I decided that this topic should be really interesting for you. And yeah, so today's topic is Schnorr signatures, and so we're going to dive into the definition of it, what's the practical usage of it, and why it's cooler than ECDSA signatures that are widely used in Ethereum. And also we'll dive deep into practical implementation of Schnorr signature checks on Solidity. Before I start, just quick organizational thing. So I will be asking after each slide about the questions. So if you have some questions, just don't hesitate to ask. All slides are really technically very deep and a lot of information happening on them. So it might be, and some of them are a little bit messy. So it might be a problem to grasp what is going on there. But if if you have questions, just don't hesitate to interrupt me and ask. Okay, so I think I can start sharing my screen now. Can you hear it? Can you see my screen? Yeah, okay, cool. Okay, so as I already said, today's topic is Schnorr signatures. And like sign-in algorithms, they can be implemented in different ways. So the way that I am going to cover today is BIP 340. That stands for Bitcoin Improvement Proposal, the number of Bitcoin Improvement Proposals. So that's a Schnorr signature standard that was adopted by Bitcoin blockchain, and it was introduced to Bitcoin with Taproot update soft fork that happened in 2019. Okay, so that's agenda for today's lecture. So first, we're going to dive deep into the definition of Schnorr, but before that, we will do small recap on elliptic curve operations, like the cryptographic primitives that stand behind every sign-in algorithm, and also we'll cover some specifics of exact BIP 340 implementation of Schnorr. And after that, we will learn the most interesting feature of Schnorr signatures. That's the linearity property. So we will see how it comes up from the definition of Schnorr signatures, and then we will cover like practical implications of that, like why this linearity is really cool, and why these ECDSA signatures, why the Schnorr signatures are just better than ECDSA. And the last section of this lecture, that will be solidity implementation of Schnorr signature checks. And there are two types of implementation. There are two ways to implement it. One is naive, where we just use formulas on Schnorr signatures and implement them in solidity. And we will see that this is super inefficient in terms of gas. So the gas cost is really super high for that. And so we will also cover the second way, how to implement Schnorr signature checks through the EC recover cheat code. And this EC recover is much, much cheaper in terms of gas. Any questions so far? Oh yeah, and in the chat, someone asked me about Frost. So Frost is another algorithm for threshold signing with Schnorr signatures. So if we will have some time, we will cover that a little bit, maybe. Okay. So if now there is no any questions, so let's go directly to the operations on elliptic curves. So in elliptic curves, there are two types of entities. One is just scalar, that's like just a regular number. So with regular numbers, we can do addition, we can do subtraction, we can do multiplication, and we can do division. All of that is happening inside the group on the prime number, the very big prime number. So when we do a multiplication of two numbers, the resulting number actually is a reminder on the division of this result on a big prime number. Okay, so with scalar numbers, it's pretty straightforward, nothing super fancy. But then there is another entity which is a point on elliptic curve. So elliptic curve, it's I have a formula here. Yeah, so particular elliptic curve that I'm going to discuss today is SECP 256K1 elliptic curve. The same elliptic curve is used in Ethereum signing, and it's widely used in Bitcoin as well. Yeah, so the same elliptic curve is used in Schnorr signatures, implementation of Schnorr signatures that we will be covering today. So the formula for this elliptic curve is y squared plus y squared equal to x to the power 3 plus 7. So that's basically the polynomial of degree 3. And here is the blue line, that's graph that's a chart of this function. Yeah, so for points, that's actually the exact like point on this two-dimensional space. So that's the point that lies on this curve, on the blue one. And with points, we can do additional and we can do subtraction. So for addition, we take 2 points A and B, and then we cross a line through these points A and B, and this line will intercept the curve of elliptic curve in another point C. So result of addition, then we take inverse of C. Inverse, that means that we take the y coordinate with minus value. So the result will be the result of addition with the point C that is symmetric to the x-axis and lies here, symmetric to point C. Okay, but that's actually really not super important for us. Just we need to know that we can add points and we can subtract points. So we cannot multiply point by point, so that separation is just not defined. And we also cannot divide point by point. And yeah, then we also have operations with scalar and points. So we cannot add scalar to point because it's just different type of object. And we cannot subtract scalar from point or point from scalar because again, it's really like different objects. But we can multiply point by scalar and we can divide point by scalar. Multiplication is just defined in the same way as like with regular numbers. So if b is 5, for example, then that means that I need to add point a to plus a 5 times, basically. So I will get the result of this operation in 5 times point a. And the whole cryptography is based on the fact that when you multiply point by scalar and you receive another point, that's the result of this operation. So you cannot, and if even you know the point, you cannot get the scalar efficiently. You cannot calculate it. So if you know the result of multiplication and you know the point, so given that information, you cannot derive the scalar value efficiently. So you only can do it like using the whole computational power of the whole humanity. And if you use it for billions and billions of years, then you will be able to find the scalar number. But of course, no one will do that. So the whole cryptography is based on this fact. So you cannot recover this scalar number after the multiplication. Okay. Yeah, any questions so far? No? Is space okay? Everything is like clear, or should I repeat something? Amit, you're
A moment, I'll add Ram as well. He wants to ask a question, I think.
Yeah, go ahead.
Yeah. So you talked about these elliptic curves. I'm just kind of how are they related to signatures? I'm still a bit kind of. You now talked a lot about this math stuff, and if you can clarify how it relates to signature, like why do we need to understand it in order to talk about Schnorr signatures?
Yeah, of course, sure. That actually was my next slide. Yeah, so when we know these basic operations with points, elliptic curve points, and scalars, then we're going to use it in the definition of Schnorr signatures. So here is exactly how we're going to use them. That's Schnorr signature, sign-in, and verification. Okay, so when you sign, you usually sign with a private key. So private key is a scalar number. It's have 32 bytes, and it's here, D. D is a private key. So when you sign some message, usually in signing algorithms, you create some random nonce, and this random nonce is used to create a signature. So this random nonce is created here. So we create a random number just the same way as a private key. So it's also 32 bytes. It's like you can also say that this is a private key, but this is actually not a private key. So like the definition that it's nonce, but it's the same number as a private key. So it's K. And then on every elliptic curve, there is a generation point. Generation point basically is a constant. So that's like widely adopted one point on the curve. That is like using that point, you can generate any other point by multiplying this point into some scalar number. So that's, but for the sake of this lection, it's just a constant point on the curve. Okay, so then we multiply k, which is a nonce, to this point g, and the result is r. So r is the point on scalar on the elliptic curve, and then when we have this r, so that's the k is just random number generated, and then we have a r, and the r has y coordinate and x coordinate. So after we got this r, we need to compute the following number s. So s equal to k, which is just number, plus, then we use a hash function, and we hash x coordinate of point r plus concatenation x point or x coordinate of point p and concatenation m. M is a message that we're going to sign. And P, I didn't talk about it, but P is a public key. Yeah, so public key, yeah, I didn't cover it here, yeah. Okay, so public key is derived from private key the same way as R point is derived from K nonce. But instead of K, we use D. So we take a private key, multiply it by a generation point G, and we will have another point, which is P large P. This large capital P, this capital P is a point on the curve, and it is a public key. Okay, any questions so far? Because it's kind of a little bit complicated stuff, so I want to make sure that everyone grabbed it before continuing.
Yeah, also, so the signature, I'm still kind of trying to relate what you talked about, the elliptic curves, to the signatures and the math. Like, maybe you could, I don't know, I think it's just a lot there, but the signature, what is it actually? Like, it's bytes, it's a number, how to think of it?
So signature, it is basically 64 bytes. In the first part of signature, so signature can be broken down or split into two parts: the first 32 bytes and the second 32 bytes. So second 32 bytes is just S. That's the number that we computed here. This one. And first 32 bytes is just X coordinate of the public key R. R actually is not a public key. It's kind of like a public key of private key K, but so it's actually a random nonce. So that's nonce point, K is nonce. So we take X coordinate of R, of nonce point R, and just add, like, concatenate with S. And as a result, we get 64 bytes. And this is a signature of message M. And message M is like, it's here. So it is hidden in hash function here.
And what is the message itself? It can be a string or anything like that?
Yeah. Message is anything that you want to sign. Yeah, in crypto, in crypto world, usually with signature, we sign some transaction. Like, for example, in Ethereum, you construct a transaction which composes of address that you're going to send the transaction, like Ethereum value, how much Ethereum you want to send to that address. If the address is smart contract, then you specify call data to that smart contract, and everything is packed as a message, and then you sign this message with a private key that you have, and then you publish it in Bitcoin blockchain. And Ethereum blockchain. On Ethereum blockchain, the smart, basically it is built that the signature is checked against your address. Address is basically your public key with some simplification. So public key is known to everybody, private key is known to you, so private key control your crypto. So if this transaction check, signature check is successful, that means that you are authorized to spend to actually execute the transaction. So you can spend from the address that you send it, some Ethereum or calls a smart contract or whatever. Yeah. So that's how basically signatures are used in crypto and checked. Did I answer your question? Okay.
Yeah, at least mine, yes.
Yeah, cool. Okay,
Thank you.
great. Yeah, so, okay, so as for now, we just look at this formula and we cannot like get why we actually choose that formula and not other formula for creation of this signature. So it's kind of like not intuitive, but here is how we verify this signature, and the verification is very simple, and which is more important, the verification is linear in terms of private keys. So about linearity, I will talk a little bit later, but now we can see how these formulas are actually used to verify a signature, and maybe that will give you a little bit more clue why we actually choose this formula. Okay, so in order to check a signature, so we have basically four values. First one is x coordinate of nonce point here. The second value is s, that was computed here. Third value that we know is the public key of signer, and the signer signed with private key here, D1. And the fourth value is message itself, the message that we are signing. Okay, so to verify a signature, we need to do the following. We need to compute capital S, which is x coordinate of nonce point, which is known to us. And then we do hash of x point of nonce point, x coordinate of nonce point. Concatenation x point of public key, p capital is a public key, and then we concatenate with this message that was signed. Okay, so all of this value we know, so we can easily compute the hash, and also we know p, which is public key of signer. Okay, and when we compute this capital S, so we actually need to check that this S, small s, times G equal to S that was computed here. What does it mean? Okay, this is the hard part. Yeah, so S is a scalar number, so we actually can treat it as a private key. If we treat it as a private key, that means we can create a public key of it. So creation of public key of small s will be S multiply the generation point G. That's always the way how we create a public key from the private key. So yeah, again, it's not the private key actually, but we can treat it as a private key. So we can like use the same operation here. Okay, and then if
Slava, can you say a few words about this process? Like, why is G used to create a public key using S?
That's how cryptography is basically built. Like, I mean, remember I told you before that when we take a scalar number, which is basically 32 bytes, and multiply by point, point multiplied by the scalar number, then we receive another point, and knowing the generation point g, and knowing the resulting point, we cannot extract the scalar number. So
because it's a linear curve, so taking
yeah,
a point on
yeah,
the curve and multiplying it by scalar is also on the curve.
yeah.
Okay, so yeah, I get it. Thank you.
Yeah. So when you so using this property, the public key can be shared among everyone, where, like, without the, so you don't fear that your private key will be leaked, because if you know the public key, you cannot extract the private key from it. So that's exactly how it is how this feature is achieved here, because you take a private key, multiply it by generation point g, and you will receive a public key. Yeah, but usually public key is actually it's a point on elliptic curve, but usually people just use one coordinate of this point. It's x coordinate, because y coordinate can be easily calculated from x coordinate. So you don't need to use two numbers because it's going to be 64 bytes. You use just one number. It's shorter, only 32 bytes. Okay, so going back to the formula. So in order to verify, what you need to do? So you have S, and you can calculate capital S. Capital S is just S times G. It's here. And then you take R, which is nonce point here. And this hash is known, so you also can calculate this, and the public key is also known, so you can calculate the expression here on the right hand side. And then what you need to do, you need to compare these two numbers. If they are equal, then the signature is correct. If those numbers are not equal, so then the signature is not correct. So, and the proof of it, it's a little bit complicated, yeah, but it can be boiled down to this expression. So basically, what we take the expression from here, which is S, the definition of S equal to K plus times a hash function on this value times the private key D. So we take this expression and we multiply both sides by generation point G. So we will receive SG, then K times G, here is K times G, then the hash function remains the same here, and we have a D and times G. And now we can just see that K times G is equal to R, which is here, and D times G is the public key, which is P. Yes. And S times G is a capital S. So yeah, so if that equation is correct, then this equation is going to be also correct. So that's very simplified proof of why Schnorr signatures verification is valid. Okay, yeah, among the validity of Schnorr signatures, there are also a bunch of different other properties. And I think, yeah, any questions so far?
Yeah, I guess it's a bit less related to the verification of Schnorr, but I'm just kind of trying to, like, how is it related to the liquid risk-taking in Bitcoin or on Bitcoin, or however you would like describe it?
Okay, yeah, so I think this is, yeah, go ahead, sorry for interrupting.
Yeah, no, so yeah, like, what is the need? I'm still kind of having a hard time seeing why use like Schnorr signatures, and I don't like what is special about the scheme and how it relates to Bitcoin and liquid risk-taking.
Mm-hmm. Okay. Yeah. So I think I'm going to skip this slide because there's a lot of math here. And let's talk about the practical applications of Schnorr. Yeah, and why we use Schnorr signatures in our Bitcoin liquid staking protocol, and actually why Schnorr signatures were introduced into Bitcoin blockchain in 2019. Yeah, because Schnorr signatures, if we compare it to ECDSA signatures, so first distinction is that Schnorr is just mathematically simpler. I mean, it might look like very complicated, but if we take ECDSA signatures, that is common signatures on Ethereum blockchain, they are much more complicated than Schnorr. And the problem is that beyond the verification property, you also need to make sure that that the signature cannot be forged. That means that you cannot create a signature that is valid without using a private key. And this property is really hard to achieve. And it's really very beautiful. The beauty of Schnorr signatures is that it's a super simple scheme that cannot be forged. Because naive schemes, like, I don't know, they either can leak your private key when you do a signature, or the signature can be created without the knowledge of private key. So it's really hard to come up with such simple sign-in scheme as a Schnorr that is secure from the cryptographical standpoint. Yeah, and some others like properties that actually ECDSA signature is not fully proven that they are secure, and Schnorr has a like mathematical strict proof that this is secure under standard assumptions. And the ECDSA is not linear, so you cannot make a multisig. And Schnorr are linear and can't make a multisig. What does it mean? So before Schnorr signatures on Bitcoin blockchain, multisig was implemented in the following way. So you can unlock some UTXO on Bitcoin blockchain by providing k out of n signatures. And those signatures are like, and every public key of the signatures that's going to be checked needed to be recorded in UTXO. Every signature, every public key is 32 bytes. So basically, if you use 10 signatures to unlock your UTXO, then your transaction is going to be 320 bytes, at least. Because you need to record all of these public keys. And when you do the sign-in, every signature is 64 bytes. And then 10 times it's going to be 640 bytes. So it's a lot for Bitcoin transaction. And that's only like the script that's going to unlock UTXO and also some other. So it's actually more than 640 bytes. And with Schnorr, you can implement a multisig with only one public key. So you don't need to record every public key that is going to be used to check a signature. You kind of can aggregate all signatures into one signature, and then only one public key going to check this one single signature. That is combination of your multi-sig signatures. And that drastically decreases the Bitcoin blockchain space that is needed for your transaction. That's the first reason. And the second reason is the privacy. So with traditional multisig, when there is a public key for every signature that's going to be checked, you kind of like know who exactly signed the transaction. But with Taproot, you kind of can obscure that. And more importantly, you actually can tell that you cannot tell if this is a multisig transaction. Multisig UTXO or this is a single key UTXO. There is no difference how to distinguish them. There is no way to distinguish like multi-sig taproot transaction from ordinary one. Yeah, again, so with Schnorr, it's much easier to create a multi-sig aggregation because you kind of can add all signatures into one signature. You also can aggregate a public key, and then you check aggregated signature against aggregated public key. And because of that, your multi-sig transactions much smaller than it used to be before on Bitcoin blockchain, at least. Yeah, I mean, on Ethereum, multi-sig transactions are also implemented in a way that every signer actually needs to sign, and then the signature is recorded on Gnosis safe, for example. And then, like, for example, you have 3 out of 4 that need to approve the transaction. Then if you have 3 signatures, only then the final transaction is approved. But it's every signature is 64 bytes, so you use a lot of blockchain space, like block space. And as a result, you also use more gas to implement that multi-sig. So with Schnorr, all of that multi-sig logic is compressed into one single public key and one single signature. So it's only 64 bytes for a signature and 32 bytes for a public key. Questions? Okay, so just to recap, so Schnorr signatures allows you to create a multi-sig that is much more efficient. So it creates smaller transaction and the verification is faster because you can aggregate all signatures into one and aggregate all public keys into one and then check the aggregated signature against aggregated public key. And also the privacy is better than ECDSA signatures. Yeah, so why we use Schnorr in our Bitcoin Liquid staking protocol? So the reason for that is that the efficient way to make a multi-sig, so basically, like we need to create a bridge for our protocol that is like locking the liquidity on Bitcoin side and then issue a wrapper token on Ethereum side. And in order to manage liquidity on Bitcoin side, we need to implement it as a multi-sig because there is no like complex smart contracts on Bitcoin. Some people actually working right now on BitVM, which is a really interesting topic, but is out of the scope of today's lecture. So that's a way how to implement some sort of like smart contract for a bridging on Bitcoin side, but it's really hard and a lot of complexities there, and the transactions there are really super big and super expensive. And the only efficient way to implement the multi-sig on Bitcoin blockchain is using Schnorr signatures, because we can implement some threshold signing like K out of N of private key holders need to sign in order to release funds. And this can be efficiently done only on taproot addresses which implement Schnorr signatures and Schnorr public keys. In contrast, on ECDS, so this threshold signing algorithm that we use, it only uses 2 rounds to actually create a signature, whereas almost the same algorithm that works on ECDSA will require more than 5 rounds, and I think closer to 8. So like 2 rounds and 8 rounds, it's a really huge difference. And in our protocol, the speed is crucial. So we need to sign very fast, very quickly. So we cannot do it in 8 rounds. because 8 rounds is really like, I don't know, maybe 10 seconds or something like that. That's a lot. So we need to sign in a second. So that's why we use Frost. Frost is this threshold signing algorithm for Schnorr signatures. Yeah, so that's the practical usage of Schnorr in, at least in our project. And hopefully you guys, after this lection, will be interested in this cryptographic scheme and may come up with some other application of this really beautiful technology. Okay, so that's about implementations properties and why Schnorr signatures are cool for Web3 development. Do you have any questions?
Yeah, I would like to understand if Schnorr signatures are exclusively working on proof of work, or it's more general use in cryptography.
No, it's general use in cryptography. So it's basically any blockchains that understand basic commands can implement Schnorr signatures. In Bitcoin, for example, it is harder. Like, you know, that the Ethereum is kind of like Turing complete. Bitcoin is not Turing complete. So on Bitcoin, implementing some operations is hard. So the scripting language of Bitcoin is really very narrow, and Bitcoin developers did that specifically to narrow down the attacking surface. So the security of Bitcoin is very high because of proof of work, but also because of really simple simplicity of scripting language that Bitcoin has. Yeah, so like scripting language of Bitcoin is kind of solidity on Bitcoin. So it's a way to code some smart contracts on Bitcoin. Yeah, there is no smart contracts on Bitcoin, of course, but there is some functionality that allow you to create some more or less complex scripts that can be embedded in Bitcoin addresses. Yeah, so before 2019, there was no possibility to use Schnorr signatures on Bitcoin, but in 2019, Taproot soft fork was activated on Bitcoin blockchain, and after that, Taproot addresses and Schnorr signatures and Schnorr Schnorr sign-in addresses became available on Bitcoin blockchain. On Ethereum, there is no native support of Schnorr signatures. However, there is a library that implements checks of Schnorr signatures in Solidity. And that's the next topic of today's lecture. Yeah, so here I actually have various snippets of Solidity code that actually implements the Schnorr signature. I don't know, it's super technical and super detailed. So do you feel okay to go through it, or I just can like go through it very quickly?
I think you can go through it quickly, but if that's okay, we would love to upload that as well after the lecture, so people will be able to review it themselves.
Yeah, sure. I will share all the links that I used in preparing of this lecture, so everyone can.
Awesome. We'll make sure to upload it as well.
Yeah, cool.
Thank you, Scott.
Okay, so then really quickly. So this is based on where is the source? Yeah. So this is based on the Zero DAO Finance library that is called BIP 340 Solidity. So that's implementation of the Schnorr signatures that are specified in Bitcoin Improvement Proposal number 340. So that's compatible with Bitcoin. Yeah, the other reason that I did not mention why we actually use Schnorr signatures in Solidity, because our project is built on top of this multi-sig scheme, this cryptographic multi-sig scheme. So we want to have it like uniform across all different platforms that we use. So we use Bitcoin platform and Ethereum platform. And on Bitcoin, we kind of like limited to use the Schnorr signatures and Schnorr threshold signing. And then like when, for example, approving mint operation on Ethereum side, we actually want to use the same scheme. We don't want to use another scheme, multi-sig scheme, because another multi-sig scheme will create more attack surface. So that's why we want to stick to a single multi-sig scheme, and that's why we implemented this in Solidity. So, I mean, like we didn't implement it by ourselves. We use this library made by ZeroDAO Finance. Okay, so first of all, let's see how Schnorr signatures can be checked in naive way. Naive way is like just using the formulas from here. So we use this formula to verify. And here is implementation. Okay, so I'm going through it very briefly. So first of all, we compute challenge. So compute challenge is function here. So basically, that's a hash value of nonce point, public key, and message. So that's so we do a hash of message, and that's a challenge. But also we include the information about public key and the nonce point. So this message kind of bound to the signer and to the nonce point that is generated. Okay, and then we need to do 2 multiplications of scalar number to the point. So it's here, electricity curve dot jackmul. And jackmul is Jacobian multiplication. So it's transform. Remember the point on the elliptic curve is 2D point, like on a plane, but Jacobian transformation transforms this point into 3D, like not in a plane, but on the I forgot the word on the volume.
Another point on the z-axis that is connected to the x and y, right?
Yeah, like that third coordinate. So let's create a third coordinate, and then we can do the multiplication of this 3D point on the number, and it's more efficient than if we just do a 2D multiplication. So that's just basically for gas, saving the gas. So that's why we use the Jacobian transformation and Jacobian multiplication. Then after that, we check basically that the 2 points that we received here, they are not equal to each other. Because if they're equal, we cannot use traditional addition of these 2 points. Referring back to formula here. So we have 1 point here, R, the second point, this one. So H is a scalar, P is a point, so we multiply point by scalar. Then we have 2 points, and we need to add these 2 points. But if these 2 points are by chance equal, then we cannot use traditional addition. We need to do a double duplication of the point when we add point to itself. It's a slightly different operation, so that's why we cannot use a traditional addition.
Why is that, Slava? Like, why we cannot add the same point twice? Does it not just like double the x and y variables?
Because when you have 2 different points, you can draw a line through these 2 points, and then you will have the third point here. And then the third point here, coordinates can be easily calculated if you know the coordinates of these 2 points. But if you have A equal to B, then you kind of draw not a line that intersects the curve, but the line that is tangent to this curve. And then this tangent line will intersect the curve in the other point, but formulas that is used to derive this coordinate of this point C, they will be significantly different from those formulas, so that if these points, they are distinct.
Okay, thank you.
Yeah, no problem. Okay, so we check if these 2 points are not equal, but actually the chance of that is really, really small. but we need to have this check, because if you don't have this check, then someone can create a signature that will go through this check because of this, because they can just like forge some values that are equal here, and then we cannot use the addition. So if we have this property, we need to return false. So the check is false. Okay, and after that, we do additional like inverse of the point y, and then we do Jacobian addition of 2 points on the curve. The points that is r here, r and point h time p. And when we do the addition, then what we need to do, we need to check, oh, sorry, that's a different one. Then we need to check that the points that we have here as a result equal to small s times g. Yeah, so here is that's the conversion back to 2D space, and then we check. I think that the check didn't get into this slide. Yeah, the check that small s times g equal to the points that we get here. Okay, that's naive, and I want just to show you how much gas does it have, does it use. So here I have like 2 contracts. One is that implements naive, and the second one that implements gas efficient way to check Schnorr signatures. So okay, so that's gas efficient. Okay, that's naive. Okay, so I put here some signature data that is going like correct signature, so that returns true. I'm going to call it. Yeah, and just check how much gas it uses. So it uses 2,325,000 of the gas. So it's really a lot. So 2 millions, I don't know, it's maybe will be, I need to do a math, but it's more than $100, definitely more than $100 of the transaction fees. Yeah, so in comparison, now let's check how much gas we'll use, gas efficient way to calculate that. So gas efficient way is used just 41,000 of gas. So it's like 500 times less. Yeah, something like that. Yeah, so how we can achieve that efficiency with Schnorr signatures? So in order to do that, we just use EC recover cheat code. Yeah, but before going to that, just again, do you have any questions? Okay, I think.
By the way, everyone, I opened the mics. If you want, you can just jump in and ask any questions you have. But you can continue, Slava. Thank you.
Yeah, cool. Okay, so first of all, we need to understand why this naive way takes so much gas to perform. And the problem lies here in this Jacobian multiplication and this Jacobian addition. And Jacobian addition is kind of a little bit take less gas than multiplication, but multiplication takes a lot of gas. So we want to avoid using this Jacobian multiplication. And actually what we want to use EC recover. So EC recover is basically the way to recover the address from the signature. So if there is some signature, but it's done on ECDSA signatures. So there is this ECDSA signature, and so we want to know who exactly signed that message. So if you know message and the signature, so EC recover tells you which address actually signed this message. And that's a cheat code that is implemented in Solidity. And because in Solidity checking signatures, it's required a lot, It was, so it's computationally expensive operation, but it costs not too much gas because this operation is used in smart contracts very often. So that's why this operation is really cheap in terms of gas. So we can, but the problem is that this operation actually implements the recovery of ECDSA signatures, not the Schnorr signatures. That's the problem. So we cannot use it like in direct way. So we need to come up with a cheat code how to use EC recover. And in order to use that, we just need to create this fake signature that is calculated from the Schnorr signature, but it's composed in a slightly different way. So I'm not going to like deep dive into how exactly it's composed. The math behind it can be found here, and here is a resource of it. I will share it after the lecture if someone wants to dive deep into that. Yeah, so how we do it here? First of all, we take a public key that we're going to check the signature against this public key, and we convert it to fake address. Fake address, that means that like we treat this public key as a regular public key for ECDSA signatures, and we convert it to the address as if this public key was just regular ECDSA public key. And the resulting address, we record it, and then we do all of these magic tricks with Schnorr signature to be able to use EC recover. And then we calculate EC recover and then just check that the address that we received from EC recover is equal to the address that we received from fake conversion to the fake address. Yeah, so function looks like much simpler than before. Yeah, here it's a little bit more complicated. Yeah, here is simpler, but the trick is these formulas. So they are not like straightforward, and math behind these formulas can be found here. So this resource I will also be posting after the lecture. Yeah, and as I already showed you that because of this trick, we saved like 500 times less gas.
Does this trick create any vulnerabilities?
Yeah, that's really a very good question. Yeah, so it creates, it slightly reduces the strength of signatures because basically Ethereum address is 20 bytes and Schnorr public key is 32 bytes. So when we do conversion of the public key to Ethereum address, like we kind of like shrinks the 32 bytes into 20 bytes. And breaking something of 20 bytes is much easier than breaking something of 32 bytes. So the more bytes you have, much harder it break, because like in comparison, 2 to the power 20 is much less than 2 to the power 32. Oh, not actually 32, but 256, because you have 8 bits each byte. Yeah, so 2 to the power 256. However, on practice, it doesn't reduce, like that's in theory, like in terms of, some science and so on. But in practice, it doesn't reduce, doesn't create any vulnerability, because still, even for 20 bytes, it's still impractical to forge a private key that will be like that will break the signature.
Okay, and this is only for Ethereum?
This can be used on any EVM blockchain. So all L2s, Ethereum L2s that are compatible with EVM, also, of course, you can use this Solidity code. For Solana, since they use Rust, so this library is not cannot be used. And for Solana, I personally, I don't know any libraries that implement Schnorr signatures, but should be there because Solana is using Rust, and as far as I know, at least like Frost implementation, there is a Frost implementation on Rust, so should be some libraries that compatible with Solana to check Schnorr signatures as well. Okay. Any more questions?
I think we're good in the meantime.
Okay. So I just want to give some credits to people who created this Schnorr workshop that I used before. All of these slides were taken from the Taproot workshop. So there are like more than 100 contributors into that. So that's a workshop that was created by Bitcoin community and to educate developers to work with Schnorr signatures to like make life of Bitcoin builders easier. So Bitcoin builders can build something on Taproot that was introduced in 2019. Yeah, and I also want to credit Trey, who developed this BIP 340 Solidity library from Zero DAO. Really a very smart guy. Okay, so that's it for today. Yeah, I kind of like have a few slides about Frost, which is threshold signing multi-sig scheme for Schnorr, but again, it's a lot of additional mathematics on here. So I think if no one requests to go through it, so I think I will skip it for today.
Okay, thank you so much, Slava.
Yeah, thank you for inviting me. And
Awesome. And just before we finish, we would like to ask you a few questions if you would like. Maybe on like how did you get onto in the Web3 ecosystem? How did you start? Maybe tell us a little bit about yourself. And yeah.
yeah, sure. So I start my crypto journey in 2015. So I was hired by Bitfury Group. That is a big mining company, used to be in 2015. Then they kind of like, yeah, the competition on mining space was tough. So I was hired by Bitfury Group, and at that point I didn't know anything about crypto, about Bitcoin, about anything. So they just like gave me the Bitcoin white paper and Lightning Network white paper and said, read it, go through it, and then tell us what do you think. So that's how I read my first paper, Bitcoin paper, and the second paper was Lightning Network paper. And as you maybe know, so we currently build our project on Lightning Network, based on Lightning Network. Yeah, so I really already like almost 10 years into that technology. So that's how I start my journey. And they said, okay, so we kind of like mining company, so we want to Bitcoin be adopted worldwide. So they were thinking about like scaling solutions to Bitcoin because apparently already in 2015 it became apparent that Bitcoin is not scalable. So yeah, that's how they found the Lightning Network, which is Bitcoin scaling solution, and they hired like 10 people to like to work on the technology, to help with adoption of the technology, because I thought that this will increase adoption of Bitcoin. Yeah, so I spent 3 years there, and I was like purely focusing on Bitcoin. So that's on that day, it's like Ethereum start to evolve, and many other blockchains like EOS, IOTA, a lot of different stuff. Yeah, but since I was working on Bitcoin mining company, so I was really focused on only Bitcoin, and did not pay attention too much on what happened on Ethereum side. But so that was a big mistake, I think. Yeah. So after that, like I crypto winter, like we all faced crypto winter. So a lot of people were fired, and including me. And I started looking for a new opportunity, and I started paying attention what's going on the Ethereum side. And when DeFi summer kicked in, I was working on several projects with people who I met before, and that's how I start working on Ethereum and learn Solidity and start pay attention to broader crypto ecosystem. Yeah, and after that, I had a few successful personal projects, really projects from 1-2 people. Few of them was trading on dexes and doing some liquidation stuff. Yeah, and after that, my friend came to me and told this idea about liquid staking on Bitcoin because he was working at Lido. And he said, cool, Lido did a great thing for staking on Ethereum, so let's do staking on Bitcoin through the Lightning Network. And I oh yeah, that's a great idea, let's do it. So that's how we started doing Strum. And already 3 years working on that.
Awesome. About your experience building on Bitcoin, as you might explain to us yourself, the community is very cynical or considered hard. What was your experience building on Bitcoin?
Oh, yeah, it's very good question. Yeah, a lot of people on Bitcoin, they're super conservative. And for example, I visited a Lightning Network conference recently, and one guy was describing, hey, I came up with new design of the bridge, and was just telling about something like wormhole, which is already live on Ethereum for a long time. Yeah, so people on Bitcoin, they're kind of a little bit, I don't know, conserved within their ecosystem, uh, but not all of them. Yeah, a lot of people start looking what is going on in Ethereum, and on Ethereum, basically innovations happening much faster than on Bitcoin, and that's actually is by design of Bitcoin. Yeah, Bitcoin is designed to be immutable, so it's really hard to change something on Bitcoin because the biggest value proposition of Bitcoin is immutability. That's why everyone loves Bitcoin, because it's immutable. So there is no the changes that introduced into consensus. They are so rare. They are so battle tested before the introduction. So everyone is, and all of them backward compatible. So all of them are made through the soft fork, not a hard fork. So from the one hand, it makes Bitcoin really, really super secure. For example, every update that's happening on Ethereum is done through the hard fork, and if something goes wrong, then Ethereum blockchain can fork, and there will be two blockchains, and then it will be hard to to connect all of them. Yeah, so Ethereum took a riskier part. So all of that updates are much riskier, but the innovation happening much faster than on Bitcoin, and that's really a struggle for me. I like what is going on Ethereum because all of these updates and all of the developer friendly stuff. On Bitcoin, developing is really hard, much harder, much slower, and yeah, but that's why actually everyone loves Bitcoin, because it's immutable.
Awesome. Another question is about Lightning Network. I know it exists for quite a lot of years now. So, what do you think is kind of holding it back from, from exploding, or
Yeah, also good question. um, so on Lightning, it was designed to scale specifically Bitcoin. So there are some design decisions that are not intuitive for ordinary people. For example, Lightning heavily relies on payment channel, And in order to pay or receive, you first need to open a channel. So it's kind of like opening a bank account. And this operation is done on chain, on Bitcoin blockchain. But like when you open an account on bank, you can receive unlimited amount of that bank account. I mean, if government doesn't block it or whatever. Yeah, but on Lightning, when you open the payment channel, and this payment channel has a size. So if it's like 1 Bitcoin, you cannot receive more than 1 Bitcoin. If you want to receive more than 1 Bitcoin, you need to open another channel, and someone need to put liquidity into that channel. So this like not intuitive customer experience with payment channels led to some delays with adoption. However, lately people realized that, okay, we need to somehow abstract that away from users, and they created a really user-friendly applications, for example, Wallet of Satoshi, Galoy, which overcomes that. And that's created, like that boosted adoption of Lightning a lot. But after that, I believe that Lightning hit another wall, which is basically because of small TVL in Lightning Network. So because of these payment channels, in Lightning Network, you can send the payments only through these payment channels. And basically, if there is small number of payment channels, then transaction volume that you can send is small. If the amount of payment channels and their sizes are bigger, then you can send more through this Lightning Network.
It is proportional to the size of the network?
Yeah, because the scalability of Lightning Network basically correlates with the size of the network. Yeah.
And is it linearly dependent or?
No, it's not linear, but in first approximation is kind of linear. Yeah.
Okay.
So basically, if you hit this, the payment volume goes through these channels, goes, and then they hit the capacity, then users just cannot send the payment. And I recently tried to make a deposit to OKX exchange through the Lightning Network, and I just couldn't do it because capacity is limited. So my payment didn't go through, and that's the problem with Lightning. So some payments are failing because of small amount of liquidity in Lightning Network. And I believe that pouring more liquidity in Lightning is really crucial for adoption of Lightning. That's the reason why we're building Strum. So our idea is to take Bitcoin liquidity and put it in Lightning and make it more scalable, improve the throughput of it, and make the adoption of Lightning Network feasible.
Awesome. Okay, let's see if I have more questions. First of all, if any of you or the participants want to ask anything, Slava, this is a good time. Feel free to just open your mic. But yeah, in the meantime, Slava, I would love to know what is your favorite thing about the ecosystem, or your least favorite thing about the ecosystem at this moment, at this stage at least.
You mean the broad crypto ecosystem or some specific Lightning ecosystem?
You can take it anywhere you would like. Both are interesting to me.
Okay. Yeah, most favorite is amount of innovations that is happening. The people come up with a lot of brilliant ideas because a lot of new challenges started become available with crypto because people just did not use value or use cryptography in the way that people now use it in the crypto ecosystem. And that's cool. For example, Frost algorithms that I was talking about today, it was the paper about it was published in 2021. So it's only 4 years old. So for cryptography algorithms, it's really, really super young algorithm.
Yeah.
And a lot of such innovations happening, and that's super cool. And I like in any crypto ecosystem. why I love to work here. Um, the most terrible thing or the least uh, valued thing in Lightning and Bitcoin, I think that's speed of innovation. Yeah. So I don't like that innovation in Bitcoin and Lightning happening very slowly. Um, it is changing a little bit right now. For example, with introduction of BitVM, I think that's really changing because a lot of companies start building BitVM, which is super cool and super cool technology. But still, it's still slow. In general, crypto ecosystem, I also don't like how people chasing the, I don't know, like a new big narratives, and sometimes people doing something like meme coins. Like for me, meme coins is completely useless thing, and I don't understand it. But people using it, trading it, so yeah, so that's kind of like a conflict in my head. Why?
And one last thing, if you have any personal advice for developers or something you would like to share with the community that you think is valuable that you learned along the way.
uh, Always prioritize security. That's the most valuable advice I can do. I can tell.
Awesome. So thank you so much, Lava. It was a pleasure.
Yeah,
And
thank you for inviting me. Really a pleasure to talk here.
yeah, it was a pleasure. Thank you so much, Lava. And see you next time. And thank you for joining us today. And for everyone, thank you for listening and joining us. Um, and yeah, everything will be available on our website, on our YouTube channel, and also on Telegram and LinkedIn. And yeah, thank you everyone for going to this live. See you next time.
Yeah, thank you. Bye bye.
See you next Wednesday.